Okay. So last week we talked about Gaussians and their geometry, right? So remember, we looked at a multivariate Gaussian density, and we considered the covariance matrix of that density and looked at its eigenbases, the eigenorthonormal basis that I described. And we saw that the eigenvectors give us these directions here, which are, if we plot the Gaussian as contour lines, then these directions give us the semi-axis of those ellipses, right? And we saw that these contour lines, or that if we sample points from this Gaussian, they basically track the shape. We also saw that this matrix describes the quadratic form, so that's the expression that sits upstairs in the exponential in the density. And these are the contour lines of that quadratic. So now, if we now think of these directions as, we can think of these directions as random variables. Yeah. And so basically what we're doing here is the following. So this here is our this here the e's are our standard bases. Okay. So this is they're just the standard axis vectors of our Cartesian system. So now we can represent each eigenvector in the eigenorthonormal basis. Think of this as a normalized eigenvector, right? We can represent that as some change of basis. So as some linear, it's a vector, so we can write it as a linear combination of these basis vectors, right? So now, because these form an orthonormal basis and these vectors form an orthonormal basis, if we write all those coefficients into the matrix, and we get a square matrix that is a change of basis between two orthonormal bases, so it's an orthogonal matrix. Yeah. So let's call that O for orthogonal, right? So this is an orthogonal transformation between these two bases, between these two coordinate systems. And now we can represent a random vector that we sample from our Gaussian in this new coordinate system, right? It's just another vector. We can represent it in this new coordinate system. So then we get something like this here. So since each of these vectors here is a random variable, this is a random variable. So we have basically just taken our random variables and written them as vectors in the different coordinates. So now the point is, what do these random variables mean? Yeah, and what they mean is, if we have a Gaussian with mean, mu, and variance sigma, then so we can shift. First, we can shift the origin of the coordinate system into mu, right? So in the previous slides, we always just assumed for simplicity that the mean is 0. So if we're rotating something, we're just rotating around the origin, but we're also rotating around the mean. Right? Now, if the mean sits somewhere else, then we first take our coordinate system and shift it into that mean. And then when we rotate, we're again rotating. So we shift the coordinate system into the mean, then we rotate the coordinate system into this eigenorthonormal basis, okay? And then in the new coordinate system, what is our covariance matrix? It's a covariance matrix with respect to the eigenvectors, its own eigenvectors. And we know that the representation of that is just the diagonal matrix with the eigenvalues on the diagonal, right? So the diagonal entries are the eigenvalues, the off-diagonal entries are all 0. So now we have our Gaussian represented in these new coordinates, right? And so this vector here is now a Gaussian vector in with a covariance matrix that is diagonal, right? And so what that means is, and it's exactly in one of these directions here. So these are independent Gaussians, and we can think of them, if you will, as one-dimensional Gaussians, because they are each along one of these coordinates. Yeah, so you draw your vector, it's a d-dimensional vector. Think of the d entries as d separate one-dimensional variables, right? So there are no off-diagonal entries, so their covariances are 0. And because they're Gaussian, that means they're independent. Okay. So in some coordinate system, if we have a multidimensional Gaussian, then there is some coordinate system, and that coordinate system up to this shift is just a rotation or possibly re-enumeration of the x's, right? Anything that we can do with an orthogonal matrix. So up to an orthogonal change of basis, our Gaussian, no matter what its mean and covariance, is a Gaussian, a list of independent Gaussians, right? There's always, for every Gaussian, there's some other coordinate system in which these variables decouple. Yeah? Or another way to think about it is that in order to get this Gaussian, you start with these n independent variables. And then by rotating your coordinate system, you basically smear them out into something that's dependent. So this is one aspect of Gaussian magic. Yeah, the Gaussian is an absolutely magical object, and there is something in probability theory that there are certain types of random quantities where no matter what you do with them, everything always works out somehow. Yeah, so the Gaussian is one of them. The Brownian motion is one of them. The Poisson process is one of them. Yeah, there are these quantities that are like, so probability theory can get very complicated. There are certain quantities where everything always kind of inevitably works out. Yeah, and the Gaussian is one. Okay. Good so far with that. Yeah. Okay. Now we have looked at maximum likelihood estimation before. And now we look at how we do maximum likelihood estimation, in particular in the multidimensional Gaussian. Yeah. So in the multidimensional Gaussian, we have two parameters, right? We have a mean and we have a covariance matrix, and we have to look at both of them. So again, in our maximum likelihood estimation setup, what that means is we have data x1 through xn in some d-dimensional space, and now we assume a Gaussian model, right? So what that means is we assume that our model, our set of probability distribution, is the set of Gaussians. So any mean and any covariance matrix, and this here the G is for a Gaussian density. Yeah. Now our ansatz is that in ML estimation that we treat the two parameters separately, and I will write theta for parameter, which can now mean either mu or sigma depending. Okay. So either we try to estimate the mean, then theta is mu, or we try to and fix the covariance, right? Or we fix the mean and try to estimate the covariance, and theta is the covariance. In either case, the maximum likelihood estimator looks like this. We have to take the log likelihood, right? The joint log likelihood, so it's the log of this product. Then we take its derivative with respect to the parameter we're interested in and set to 0. So that means we have to take this expression here, take the derivative with respect to either mu or with respect to sigma, right? And then set that to 0. Now, if we go through those computations, then what we find is that the maximum likelihood estimator for the mean is simply the sample average. Okay, so simply the sum, the normalized sum, the average of the points that we have observed. And for the covariance, so note that that does not depend on the covariance. Right? I fix my covariance matrix, but no matter which covariance matrix I fix, it doesn't enter in this formula. So, and then there's the covariance, the estimate for the covariance matrix. So here I have the mean fixed. I assume that I know that, right? And then the formula for the maximum likelihood estimator is this here. It has to be matrix valued, right? And how do I get it? Well, I take the mean, I take my observation point, I subtract the mean, and then I take the outer product with this. Okay. And I average over those. That gives me a matrix, and I average over those matrices. One thing to keep in mind here is if I take a vector and I take its outer product with itself, then I get a matrix. What is the rank of that matrix? It's 1, right? That matrix has rank 1. Of course, my covariance matrix in general does not have rank 1. In fact, it should have rank D, right? If it has rank less than D, then it means that my Gaussian concentrates on some lower dimensional plane. Yeah. So variance matrix has rank D. This here, just one of these entries has rank 1. But from a single observation, I just can't get more than that, right? Now, in principle, if my data is sampled from a D-dimensional Gaussian, then I will have a matrix of rank D here once I've seen D data points, right? Because basically, intuitively, if I have 2 data points, I take their matrices and I want the resulting matrix here to again have rank 1, then they would have to be exactly in one plane, right? So they would have to be degenerate. So once I have, that does not happen with probability 1. And so after I have seen D data points here, I will have a rank D matrix. But that has to be taken with a grain of salt, because the rank will in principle be D, right? So it will in principle be a rank D matrix and an invertible matrix, but it could be numerically very close to not being invertible. Yeah. Okay with that? Does that make sense? So now I have a few slides in here where we actually go through those computations, right? So here I've just written out these 2 estimators. We haven't actually done the computations. And the computations are not something that I think is very useful to actually move through every detail in class, right? We will briefly look through it, but there's a slide here which is just a refresher with some formulas that are used in these computations. Because what we have to do here, we look back at the previous slide, what we have to do here is we have to take a derivative with respect to either quantity that is either a vector or with respect to a matrix, right? So you have to differentiate with respect to a matrix. And that is maybe a bit unusual for some of us. And so here's a refresher with some formulas that are used in that, just in case it's useful. But I will not force you to go through that with me in class. Yeah. So what we do here is we take the derivative with respect to the log likelihood. If we take this with respect to mu, right? Okay, then you have to walk through these computations. And if you sit down at home and look through that, then you will see that it looks very similar to what you would do in one dimension if you respect a few formulas of this vector array. So, and then what we get in the end is this basically just as in the one-dimensional case, right? So, okay, and this is the two-dimensional case. So these are just written out here in case that you want to know the details of how that works. Now, now we're going to look at a model where you use a Gaussian to do a form of linear regression, right? And this is basically this kind of our first probabilistic model. It's a very simple one, right? But it's our first probabilistic model. So what we have here is a problem where we have data, D, and it consists of observed values of some form of covariates in regression terminology, and then of responses, right? So it's a supervised learning problem in that sense, that we have observations and response values for these observations. So each of these is in general a vector. And we assume that the x values have dimension dx and the y values have dimension dy. Yeah. So, and now we assume that the y's are conditionally independent of everything else given their specific x value, right? So xi and yi and yj are conditionally independent of each other given xi and xj. And in fact, yi is conditionally independent of all x's and all other y's given xi. So, and now we want to do, we basically want to do regression, linear regression. That means we want to find a model that allows us to predict what y is if somebody gives us a new x. Yeah, and the relationship should be linear. So, and here's a model for doing that. We assume that the y's have a Gaussian distribution that is a given x, right? That has these parameters w and sigma here, and it looks like this, right? So you can see this is the Gaussian formula, right? And there, here what we do is somebody gives you the x value. Now you want to predict the density of a specific y value, right? You take the x value that you've been given, you apply this matrix to it, and you use that as the mean of your Gaussian, right? So this is a Gaussian with mean wx and with covariance sigma, right? Let me try to illustrate a little bit in the simplest case what we're doing here. So simplest case is if both of these are one, right? So if the x is one-dimensional and the y is one-dimensional. So, and then we're simply doing a form of linear regression. So, and in this picture here, the x would live down here on this axis. The y lives on this axis, right? So you get data like these points here. From this, you want to estimate the model. And then if somebody gives you a value down here, you are supposed to predict the possible density, the density values of values up here for y, right? So you're supposed to predict the y value in the sense of its density. Okay. And in terms of our parameterization of that model in this picture here, so the x is the location down here, the y is the location, the offset here, the height here, and then the w parameter is this line. The w parameter specifies the line. Yeah. So then there's one more parameter, that's the covariance matrix of the Gaussian, and that is how much these points scatter around the line. So basically what you're doing here is you draw this line, and then your model is there's a line like this here somewhere that's specified by this w. And now given x at location x, the y is distributed as a Gaussian around that line. You scatter horizontally around that line according to a Gaussian. So this here computes the value of the line at x, right? And then this here is the difference between how far is your predicted value away from the line, right? And that is the value that you substitute into your Gaussian, and then it was scattered sigma. Yeah. If you there's one other case that we can one slightly more complicated case that we can still imagine, and that is, so here we have in this picture here with the line, we have 2 dimensions, right? We have x is one-dimensional, y is one-dimensional, makes 2 dimensions. We can also kind of picture the 3-dimensional case. That would be if you say have x in the plane, and then the y is a one-dimensional value above the plane, right? So then the thing that you would fit would not be a line, you would be fitting a plane with some tilt. Okay. Yeah. Not okay with this. Okay so far. Yeah. Okay. So now, if we want to estimate the parameters of this model here, right? Then so what do we know? Somebody gives you data. So you know the x values and you know the y values. And then we treat the sigma here as a hyperparameter. So you say, okay, my scatter around that line is going to be so and so much, right? And now what you want to estimate is the line or the plane, whatever that object is, that linear trend, right? And that is specified by the w here. Okay, and let's remind ourselves so that w, that w is a matrix, right? And it takes something of size of x and maps it to something of size of y, right? So its dimensions are dx and dy. Yeah, and you have to estimate that matrix from the data. So now you turn that into a maximum likelihood problem. Or one way to do it is to treat it as a maximum likelihood problem, right? So you want to estimate this as a parameter. You write out the log likelihood. So just write out this, that is just this function here that we had seen before, right? And now you have to optimize that with respect to W. And then if you go through the steps again, then you find that the solution is a W that looks like this. So you can see it's a function that involves only X and Y, does not actually involve the scatter, right? It involves only the data. So, and here you take each location vector, take its outer product with itself, that gives you a matrix, right? You sum up all of those and then invert. That is important because here, if you sum up each of these matrices has rank 1, remember? We can't invert it if it has rank 1, right? It needs to have full rank to be invertible. So we need to have a large enough sum here, enough data points so that it becomes invertible. So, and then once it's inverted, okay, so you multiply by xi. So, sorry. So this here is an outer product. You multiply it with that and so on. Yeah. So that is the maximum likelihood approach to it. Now, another way that you can do this is take a Bayesian approach, right? So you have to, in that case, you have to put a prior on the W, and then you have to ask what the posterior is. Yeah. So how does that look? Let's say yi is scalar again, right? Just to keep it simple. And that means this matrix W is a row vector, right? So yi is scalar, but we allow the x to be multidimensional, right? So again, simplest example, the x lives in the plane, and then the y is a horizontal, is a vertical value. So, so we're just gonna write small w as a column vector here, right, of these weights. Now we put a conjugate prior on this because we're working with this Gaussian model, right? The conjugate prior is going to be a Gaussian. So you put a Gaussian on it, give it mean 0, and some concentration, right? Some covariance here. So, and now here is a computation that is done in the log posterior. Okay, so what we're doing here is we say, okay, let's say this is the posterior here. So we have our model here. It has a covariance matrix. Remember, we specified a covariance matrix for our model that was a sigma y. Now, in this case here, the y is one-dimensional, so that just becomes a standard deviation. Okay, so that is the sigma here. Then we have the data. So, and now we want a posterior on the w, right? And then in addition, because we have to put a prior on it, that also depends on how we chose this parameter of the prior here. Okay, so this here are the things we're depending on, and this here is our variable that we define the posterior with. So now we substitute that posterior in the basic equation, into the basic equation, right? So the posterior is likelihood times prior divided by evidence. And if we push that through a log, then the multiplications become additions and the division becomes a subtraction, right? And so we get log of the likelihood plus log of the prior minus log of the evidence. So this here is just the base equation in the log picture. And now this term here, you can see that this term, the evidence term, that doesn't depend on W, right? So in terms of working with W, we just regard that as some constant. Yeah? So this here is some constant. And now in terms of the W's, we see that here this is a Gaussian, right? And the W appears in the exponent of the Gaussian, right? So the exponent, the x and the log cancel out, and we get this. And then of course there's the normalization term of the Gaussian, but that again in the log becomes an additive constant, right? So that here and that the normalization terms here, they vanish in this constant. So same thing here, there's a Gaussian, you write this out, then you work your way through this, you redefine some matrices in a smart way, right? And at some point, like somebody did this calculation for the first time ever, and probably spent a long time until they found the right matrix, right? But then once you define things in the right way, you find that what you get is something like this here. And this is again, the log of a Gaussian. Yeah. So something that I want to point out here first is basically this computation allows you to neglect all the normalizations. You just absorb them all into this constant here, right? And then in the end, because this thing here, the Gaussian inside the log has to be normalized, that just works out, right? You don't actually have to determine what it is. You know, there's only its value, the value of that overall constant is uniquely determined just by this having to integrate to one. So, and then the other thing is, okay, we have now a Gaussian with a new mean and a new covariance here, and we have to try to think about what those are. And they depend on covariance here is this matrix here, right? This matrix. And you see that involves, as ingredients, involves the data locations, the scatter, and the parameter A of the prior, right? And the mean looks like this. Okay. So one way to interpret this posterior, to think about what it means, is, remember, we can use a posterior in different ways, right? And one way to use it is just to do a map estimate. So to say, okay, we use it to get a point estimate, but that point estimate is not the maximum likelihood estimate, it's the maximum of the posterior, right? If we do that here, then as map estimate, we get this quantity. Yeah. And this here is our sigma W. So what you see here is, this is, here this is a data term, right? This is basically, these are the locations of the data points weighted by their responses and summed up. So, and then here we have a matrix that is the kind of the empirical covariance matrix up to normalization, right? You see that up to normalization, up to 1 over n, this here is exactly the maximum likelihood estimator of the covariance matrix of the x values, right? So now we are adding that, we're taking that, but before we invert it, we add something to it. Yeah. Okay, and if we did not put a prior on this, if we just did a maximum likelihood estimate of this, then basically we would get something that looks almost identical, except for this term here. This is the maximum likelihood estimator. This is the map estimator with prior. This is the maximum likelihood estimator, no prior. So here we take the same matrix of the data points and invert it. Here we take that matrix, but before we invert it, we add the parameter matrix of the covariance matrix of the prior scaled by the scatter. Yeah. So what is the effect of that? Again, if this matrix here, imagine I just get 2 data points, right? And I have, okay, we're actually in 2 dimensions, but let's say I just get 1 data point, right? This is a 2 by 2 matrix. We have 2-dimensional x's. So that is not going to have, it's not going to be inverted, right? So this here is actually not defined. I can't take this inverse. Yeah. Here, I'm taking this matrix and I'm adding something to it. That is a full rank matrix, right? And so I actually can do this. So that is a form of regularization. I have a problem that is where I have a matrix that is not invertible, and I modify it a little bit so that it becomes invertible. Yeah. Now, this is a very non-numerical way of talking about it. If we say it's either invertible or it's not invertible. If you work with these things numerically, then a matrix can be invertible in principle, but it can be very close to not, right? So for instance, for a positive definite matrix, that is the case if some of the eigenvalues are very close to 0. And the effect of that is that if you invert, the inversion becomes non-stable, right? So basically, things that are very small, if you invert it, become extremely large. Directions in which the matrix contracts a lot become directions in which the matrix suddenly scales up a lot. So, and this matrix is made up from data, right? It's computed from data, and this data is random. So if you do this with a small sample, and you do this for, so let's say you draw 2 separate samples from your from your data, and they're both small, right? Then this matrix is going to be, say, close to not invertible. It's going to be a poor estimate of a matrix, of that matrix, right? And so you will end up getting, or you have to expect that you end up getting very, very different solutions from these small samples. What you're doing here is you're biasing this estimate, and that way you make it more stable, right? So you reduce the variance of the estimator that you get out, the variance with respect to your input data, but it comes at a price, and that price is that you bias yourself. Yeah. So this is a form of regularization. Yeah. This is actually where the term regularization comes from, because the matrix is singular or it's regular, right? And you're literally making a matrix more regular. That means to make it more invertible, right? Okay, so in statistics lingo, this is known as sometimes known as shrinkage. And the idea here is that what you're doing is that you are, if this matrix here is positive semi-definite, right? Then the effect of that is that it shrinks your weight vector here, your estimates, towards the mean of the prior. Okay, and if the prior mean is 0, then it means you're shifting those values towards 0. And that is called shrinkage, because in absolute value, you make it small. So you're shrinking your values. Means shrinkage is a slightly odd term for saying that you are biasing something towards 0. Yeah? But the idea here is that it adds stability at the price of introducing bias. Yeah. So, and that is also known if you in particular set this A here to the diagonal matrix with the same entries, right? So this identity matrix just times some scalar. Yeah. Then this is also known as a ridge regression estimate. Okay. So same model. Here we add a prior. Here we do maximum likelihood estimation, right? And then in the prior setup here, this is specifically the math estimate. How do we choose the A? Yeah, that's the secret sauce of your model, where you choose the A, right? There's no general rule how you choose it. The way to think about it is like what price you pay, right? What are the downsides of choosing it, right? So first of all, unless you have like some very good reason to do it, you probably want to treat all dimensions equally, right? So you probably wanted to make it a multiple of the identity. And then if you choose it this way here as alpha times identity matrix, if the alpha was 0, then you would not be regularizing it, right? Then you're basically doing maximum likelihood. So now if you make the alpha larger and larger, then the effect is going to be that you get more regularization, right? So your inversion here, your numerical inversion matrix becomes more stable, and the variance of your estimate goes down, but you're introducing more bias, right? So, and another thing that you can see here is, so this here, we noted before that this here looks like the maximum likelihood estimator of this matrix, but without the 1/n term, right? So what is the effect of that? That means that this matrix here, like the overall magnitude of it grows as with sample size, right? So, and and that means that here this matrix is constant. So as you see more and more data, this here gets in the sum, this interpolation between these two, this term gets more and more weight, right? So whatever you choose here, ultimately, you get a bias here, but ultimately your data will overwhelm that. Yeah? So, but as you can see, to choose the A perfectly, you would have to know exactly in which way this is unstable, right? Yes. Sorry, could you repeat?
Could be. Usually it might be closer to something less than 0. and that would sort of lead to some of the random collapse. That risk differential that we may help to sort of resolve that issue.
Yeah, so that is exactly how it helps in a sense. So this matrix here, right? This is something you choose as a full rank matrix, right? So for instance, in this case here, right? In this case, it's this is identity times scalar, so that's full rank, right? So, and that means that if you think of the eigenvalues of this matrix here, right? This is a symmetric matrix, right? Because it's autoproduct of a vector with itself. So its eigenvalues are real, right? But they could be very close to zero, right? And that is exactly how it gets close to being non-invertible. If some of the eigenvalues are very close to zero, that means in those directions, if you look at the eigenbases, in those directions, it's almost degenerate, right? It's almost flat. And then if you invert it in those directions, you blow up uncontrollably. Yeah. Now, if you add a multiple of the identity matrix to that, then what it means, if you add this to it, then what it means is that you're shifting all the eigenvalues by alpha, right? You're adding alpha to every eigenvalue. So the alpha is a small positive value. You basically take your entire spectrum, entire set of eigenvalues, and shift it a little bit away from zero. Yeah. Does that answer the question?
Why does this bias term reduce the variance?
Why the bias term reduces the variance? So the variance of this, what I'm talking about is the variance of this estimate here, right? So think of the data that you get as random, and then from it you compute this estimate. So that's a random quantity. If you compute it twice from two different samples, you get two different answers, right? And if the variance is low, those answers are going to be, you can expect those answers to be similar to each other. If it's high, if this variable scatters a lot, then it's going to be very unpredictable, right? So, and the scatter to a large degree comes out of this inversion here, out of the inversion of this matrix, right? And it's exactly this effect that I just mentioned. So this is a positive definite or positive semi-definite matrix. If in directions where the eigenvalues are very close to, in directions where the eigenvalues are very close to zero, you're basically, when you invert it, you divide by something very close to zero. So you get something, a very large scaling factor in that dimension. Yeah. And that number is random. So you have something very close to zero, but random, right? And that just blows these things up in this direction to very large random scales. Does that make sense? Yeah. So the bias means that this here biases you means that that it offsets the expected value, right? But the effect of that, because this here gets larger with more data, right? The effect of that is actually more visible if you have few data points. Yeah. And in the limit, it vanishes, because in the limit, think of this here, basically all entries of this summed matrix, and then of this here getting infinitely large, right? And then they scale each other correctly. But this here does not grow. Yeah. Okay, so think about it this way: if you fix your sample size to n, and now you take many samples of size n, then you can ask what is the expected value and the scatter of this estimator here, of the distribution of this estimator for a fixed n. So that is going to be biased away from the true value. But as you make n larger, that bias will decrease. Yeah. Okay. More questions on that right now? You have to digest for a little bit. Okay, so here are a few references, and I've checked that they're all still available. Yeah. So Some of them are quite useful, but they're optional. So now we're going to get on to the next topic. Are there any more questions on this so far here? Between maximum likelihood and maximum entropy. So the entropy is a statistic of is a property of your distribution, but you don't usually parameterize the distribution by the entropy. In some cases, you can translate things into each other. So in the specific case of the Gaussian, the entropy is a function of the variance or of the standard deviation, right? So you can write it as some formula in which the only quantity that you get to tune is the variance. Yeah? But you apply these things in a slightly different way, because the maximum entropy principle is something that you try to determine a class of distributions, usually, right? A type of distribution. So the maximum entropy principle would say, for instance, if I take a distribution on the real line and I constrain it to have a certain variance, then I get a Gaussian. Yeah. So, but then you can tune the variance, and that gives you different Gaussians. What maximum likelihood lets you do is then estimate a Gaussian within that class, right? So one of them is a way to determine a distribution within a class, and you cannot derive a maximum likelihood estimator among all distributions, right? You need a functional form for the density as a function of the parameter in order to derive it. The maximum entropy principle is an attempt to say, how do I find the distribution that has some of the least implicit assumptions, except for some constraints that I posit, right? So in a sense, conceptually, what you're trying to do with it is different. Does that make sense? Yeah. Yeah.
So that's things that you have to work out. When you say work out, is that just the way to transform our input such that everything is independent of each other?
So you're referring to when I said earlier that the Gaussian is kind of magical and everything always works out. Okay, that is a very hand baby remark, and I don't think I can answer any precise questions on it. It's like, it was not meant in any way as precise as that. It's just an observation that even if you venture fairly deep into modern probability, the same few distributions keep showing up. And with those, you can work out what happens even in very complicated models. And then if you go beyond those, it becomes impossibly complicated. And the Gaussian happens to be one of those. And it's just one of the reasons, I think, why, like, my kind of heuristic explanation why you keep encountering the Gaussian over and over everywhere. Yeah, and it is often so. It's often described as the Gaussian being a convenient choice, but I don't think that term it doesn't quite capture just how inconvenient things can get if you use something else on Euclidean space. Yeah. There was another question here.
When you talk about Gaussians having and direction Gaussians having and independent Gaussians, this is true in all parameter assumptions, right? This independence is
yeah. So the independence between those variables depends on your coordinate system. So in one coordinate system, they're independent. If you change the coordinate system, they become dependent. Right? They become dependent.
And because if you think that you want the random variables representing this, how can you say that the independence depends on how the system?
Yeah, think of them as superpositions of each other. They're superpositions of so in the coordinate system where they are dependent. They are superpositions of each other. But you have to be a bit careful here because they are like, what we're saying is that these D one-dimensional variables that we treat as one vector, and that is maybe where the confusion comes, that these one-dimensional scalar variables are independent in some coordinate system if you write it the right way. Right? We're not talking about two random vectors here. Yeah. Okay. So then our next topic are latent variable models. And let me start with this kind of historic slide. That this slide is really dated. I don't know how old it is, but I leave it in here because I think it's actually very useful to think about like how this concept has. So by a latent variable, we mean that we have some random variable in a model that is neither an input nor an observed output, right? So it's some kind of auxiliary variable. And we're going to look into in detail at how we can use that. But for instance, that concept is very important in modern machine learning, right? In large generative models, you basically go to some stages where you transform a variable, you transform it again, you transform it again. Those intermediary steps, those are all latent variables. So in this picture here, you see something that is called a graphical model. And we're going to use this in a purely symbolic way in this part of the class. And then it is used in much more detail in Manish's part of the class. Yeah? So a lot of that is really about graphical models. They have their own formalism, their own calculus. It's very powerful. But here we're just going to use them as kind of a symbolic illustration. Yeah? And what it means is each of these circles represents a random variable. And then the arrows represent dependence between these random variables. So, and the crucial concept here is conditional independence. So if you don't have a direct arrow between two variables like this here, right? This variable and this variable don't have a direct arrow connecting them. That means that they are conditionally independent given the other variables. And what you can see here in this picture, what is hinted at in this picture is that the variables kind of form layers, right? There's one layer here, one layer here, one layer here. You can see the connections are only between layers. So this means this layer here is conditionally independent of this layer given this one. Yeah. This is something I already mentioned last week, that grouping variables into layers is a good thing, right? If you think of these here instead of as of random variables, if you instead would think of these circles as representing deterministic variables and would drop, say, the red arrows and just have the green arrows, then this would look like a feed-forward neural network, right? So graphical models and neural networks are very similar concepts in a sense. So it's just that in one of them, the variables are random, and in one of them, in neural networks, they're deterministic. Yeah? So, and then there's like slightly different and slightly overlapping terminology that becomes more and more blurry with every year, right? So the term latent variable, at least traditionally, usually implies a random variable. The term hidden variable can mean a random variable is used for random variables and also for the hidden layers of neural networks, right, for deterministic variables. But these terminologies bleed more and more into each other because there are so many people from other disciplines pushing into the field now that the terminology just falls apart. Yeah? So in this case here, let me make a little bit more precise what this means in terms of formulas. So here we have a latent variable. Our latent variable is called Z. Okay. And now we have a variable X. Think of this as something that we're observing. Okay. The latent variable is just a tool to generate X. So we have some distribution. In order to define the distribution of X, we define some distribution on Z, and then we define the conditional distribution of X given Z. So, and then the joint distribution of X and Z is a product, and the marginal distribution of X is an integral where we take this joint and integrate out the X, right? Yeah, so That's just basic probability calculus here written out. But why would we do that? Well, it can, first of all, if we just want to get a distribution on X, and X is something very complicated, then it may be much easier to define it in steps this way. So by choosing random variables that have simple distributions and then use them to parameterize each other, than to write that distribution down as a whole. Yeah. And that is something that modern generative models do. If you want to build a generative model of an image, then it's much easier to take simple random variables and transform them and learn what those transformations are, than to just sit down and say, okay, I'm going to write down the joint distribution of a random variable that represents, a 1000 by 1000 pixel image or something like that, right? I mean, good luck with it. Okay. So that is one way of doing that. In that case, you may only be interested in X, right? There's another way of using these variables where you are also actually interested in Z, where you treat X as data, and then you are interested in Z as something that explains the data. So you're actually interested in getting an estimate of what the Z is. And we're going to look at both cases. Yeah. Something that has changed drastically, and that is why I say this picture is dated. Conceptually, this picture is actually not dated. It's very up to date. But what is really dated are these descriptors here, right? And this is something where you can see how thinking in machine learning has changed. Like 10, 20 years ago, people thought of these intermediate variables here as representing some kind of concepts that have human meaning, right? Meaning that is somehow readable to human, that matches human categories in some sense, right? So this here should be this is an image, then this could be the edges in the image, and then you could assemble the edges into objects, surfaces, right? And then you can assemble those into other like derived properties of a surface, like an illumination or so on, right? What we have learned in the meantime is that this trying to impose these kind of categories on a model doesn't usually get you very far, right? What you want to do is you want to posit a reasonably flexible model and then just let it learn, and it will find whatever it needs to find, right? And then often it's very unclear what these internal variables actually mean, or you would interpret. Okay, so let's look at a very, very simple example of how this works, right? And it's quite interesting how much is actually already packaged in this like simple of example sense that you can think of. So we're going to look at a variable here like this, a Gaussian variable with zero mean and a non-isotropic covariance matrix, right? So the covariance matrix is an ellipse, not like the contour lines are ellipses, not circles. Elongate. So, and now we're going to look at two different ways of generating this random variable. One is we just write down a Gaussian like this with a covariance like this here. And the other way is we generate a latent variable first, and then use that latent to generate our variable. And the way we do that is we generate a latent from an isotropic Gaussian here, and this is one-dimensional, right, from a one-dimensional Gaussian. And then we draw according to this. So here is our latent. We generate this latent value, and then we use this latent value to scale this vector here. And then we make a draw from an isotropic Gaussian around that point. Okay. So now see, here we have one dimension. This is a two-dimensional variable. Here we have one dimension. The latent is one-dimensional. This is two-dimensional. And intuitively, what's going on here is think of so here you see an ellipse that's overlaying a bunch of circles, right? And you can see they're all like arranged on an imaginary line here. So that ellipse here, that is a contour line of this Gaussian. And these circles here are contour lines of this Gaussian for different values of Z. If you think of the Z as an offset, a one-dimensional offset along this line. So the way we're generating from this distribution here is we're generating a random offset in this direction. Then at that location, right, the scale is given by this here. At that location, we're placing a spherical Gaussian, that is this one, and make a draw from that. And then we scatter in the plane around that line. turns out these two give you the same distribution on X. Okay, so if I make 10 draws from this, the joint distribution of that is the same as if I make 10 draws, 10 times draw, 10 times do the following, draw Z, plug it in here, draw X from that, and then start over, draw a new Z, plug it in here, draw X from that, right? And so I'm just throwing out, I generate 10 of these auxiliary variables here, but I throw them away, right? I don't actually show them to you. I just show you the outcome in the end. For you, this and this will have the same distribution. Yeah. Sorry, can you repeat that? This vector here? Yeah. So fiddling. By fiddling. You have to fiddle with the formula until you get the right scale here. Yeah? You just have to try it out. I mean, of course, the way to actually do it is you write this down first, and then you do the computation and see what comes out here. But I think that is probably, I don't think that's quite answering your question, right? What, this vector here, the 1, 1. Yeah. So I just posit my model as saying, I think I'm starting from here, right? So the vector 1, 1 here is a vector that points in this direction, right? So what that gives me is this alignment here. So, and then by scaling it by square root of 2, that gives me a scale along this direction here, right? And I could also instead draw this variable here with standard deviations. But I just say, okay, I want this variable to be 0, to be a standard normal, and all the scaling is done. Okay. So, and then I make this isotropic and work this out, and then I find that that is the same as this, right? But basically, the intuition is simply I want to say, okay, I want to have a one-dimensional direction here, and I just choose that arbitrarily as like that direction. Okay, that is the vector 1, 1, and then I'm using this here, and then I scale it, right? And so by now scaling this by something one-dimensional, I'm picking a point along this line.
They're basically the same by sampling or something you want to do.
Sorry.
When you say you work up, they're basically the same.
Yeah. So the way you really work this out is you write down the formula for the joint distribution of this, and then you integrate. That is what you have to do. Yeah. If you integrate this against this, then you're yeah. So now here's a model that is called, is known as probabilistic principal component analysis. And that is basically the model I've just shown. We're just going to integrate, we're just going to interpret it slightly different. So we have our data here, and we have our latent variable Z. And now more generally, on the previous slide, we said the data lives in R2 and the Z is one-dimensional. Now, more generally, we say the data has dimension D and the Z has dimension K. The K is at most D, and typically it will be smaller. Yeah. So, and we write this as, we think of this as a following model. We take these Z values, and then we apply some linear transformation to these Z values. So on the previous slide, that was taking these Z values and then mapping them onto this line, right, this imaginary line. And then we generate a random variable by taking that location and adding some noise to it. Okay, and the noise lives in the entire space. So in the previous picture, we would apply, we take the Z values, we apply a linear map to them that puts us somewhere on this line. And then at that point, we add two-dimensional noise. So we're scattering around the line. The noise allows us to go in all directions. This here, this map is k-dimensional. So that maps to a k-dimensional subspace. And then the noise can move in all directions in the entire space. That is the model. Okay. So we assume that there is some kind of inherent k-dimensional structure here, plus noise. What we see is k-dimensional, some k-dimensional hidden structure plus noise. Yeah. So, and here the z's are independent Gaussian variables, right? So k independent Gaussian variables. And the noise is an independent Gaussian variable that's isotropic. Yeah. So now our model for observations is, as like the multidimensional version of what you had in the previous slides, we generate the z from an isotropic Gaussian, now multidimensional. And then we generate x given z by taking this z, pushing it through a linear map, and then drawing from a Gaussian that scatters around that isotropical. Yeah. This is the picture on the previous slide is special case. So, and if we write the marginal distribution, and this is what I meant by working out that the two are the same, right? So you take the marginal distribution of x is now the conditional distribution of x, this one, integrated against this one, right? We're marginalizing out z. And that gives us a Gaussian that looks like this. The mean of this was for z. And then the mean of this with respect to z plus this, right? And I've written out the means with respect to x here. So, and that gives us a Gaussian that looks like this, right? So you have this linear map here. That is a D by K matrix, this map. So here we take the outer product of that with itself. So that is D by D, but it has rank K, right? D by D rank K. This is the generalization of taking, if it would be an outer product of a vector with itself, it would be D by 1, right? You get the D by D matrix with rank 1. More generally, you take a D by K matrix, take the outer product with itself, you get D by D, but rank K. So this is a rank K matrix, and then this is a full rank matrix, but this one is isotropic, right? It's just a scaled diagonal matrix. So this one has full rank, but less structure. This one has lower rank, but potentially more structure. So, and you can interpret this model in two ways. We're going to think about what that means in a minute. Yeah. Okay.
But there was like expectation, like the expectation was going to do so actually arguments caution, right? Like last time.
Yeah. No, this is really because of the specific way that the Gaussian is parameterized by mean and variance. Yeah. Okay. So, okay, I see that I'm slightly overdue with a break here. So maybe let's take the break now because I'm getting, before I get really into this and don't notice anything anymore. We start again in 5 minutes. All right. So could we start again, please? Hello. Hi. Okay. So now there's two different ways. There are two models here, or depending on how you want to look at it, two different ways of interpreting the same model, right? So one is that we're only looking at the marginal of this this generative process, and one is that we're looking at what is happening under the hood, under the lid, in and also look at the latent, right? So here we're only looking at the observed variables that come out in the end, and here we're also looking at the latent variables, right? This here is, if we only look at it this way, then using latent variables can be a way to assemble a complicated distribution of X from simpler component distributions. Okay? A way of just using these distributions of the latent and the conditional given the latent and so on as kind of modules that we stick together by sampling our way through them and build a more complicated distribution for the X. In this case here, we are actually interested in these Z's, in these latents as explanations. Okay, and we're now going to consider what these explanatory variables here might mean. In one hallmark of this is that here, so in this case, you can see that if we write it out marginally, then the model here is simple, and the data, the actual data that is generated by the parameters of this model is observed, right? And so it's easy to do an ML estimate here. Like, so in this case, estimation is easier. In this case here, we're trying to get information about these latents, which we don't actually observe, right? The only information we have about the latents is what we observe into, like, what values of X we observe. And then we kind of have to reason backwards through our model and think about what does that mean for the latents, right? And so doing estimation, like, these are not actually data, we're only knowing them, we only know something about them implicitly. So if we then want to estimate the parameters of that tends to get more complicated. Okay, so in the case of the marginal distribution for this PPCA model, right, we can just write out the likelihood. The marginal likelihood just looks like this here, right, where this is again our rank efficient matrix here. And now, so even if we can't get a closed form solution there, what we can still do is we can solve this by optimizing numerically, right? A maximum likelihood problem is just a maximization problem. So you can take the likelihood and throw it into an optimizer, right? Whether or not you can work out the equations, you can always throw it into an optimizer, right? So you can use something like gradient descent or Newton's method. And then there are certain, for the mixed problem in particular, so for the problem where you actually care about the latents, there's a type of algorithm that basically uses the data to make a guess what the latent variables are. And then it makes a step where it pretends that it knows those latents. Then it improves its estimates for the parameters of the data, and then from that again tries to guess the latents, right? And that kind of algorithm, it's kind of alternating algorithm. The most important version of that is the so-called EM algorithm, and we're going to talk about that in a lot of detail later, if not today. So in this particular case, in this PPCA problem here, there's actually an easier way to solve this, right? And that is something that we can see if we first look at PCA, and that is also interesting in its own right, right? So this is called probabilistic principal component analysis, not by chance, but because it's a probabilistic version of principal component analysis, PCA, right? So what is the connection between this and PCA? Yeah, and so basically it's, if we let the width of the scatter go to 0, right? So remember this parameter psi is, let me just page back here. So that is the scatter of the conditional given the latent, right? And so if we again go back to the simple picture here, remember we have this line here that is the direction of this line is described by this matrix lambda, by our rank deficient matrix. So that is our low dimensional model. In this case, one-dimensional model of what happens in 2 dimensions. And then the second dimension comes in when we scatter around that line, right? So in the width of that scatter, the scale of that scatter is the psi. So that is like just a scalar that we multiply to the isotropic covariance matrix. If we now take that, if we take that scalar to 0, then we're basically saying there's no scatter of our one-dimensional line, right? So that forces, in the limit, that forces all the observations to lie exactly on this line, right? And so effectively reducing that to a one-dimensional problem. So now if we do ML parameterization in that, then we will find a k-dimensional subspace that has maximal variance. Yeah. So here's one way of writing that. So suppose we have data x1 through xn, and let's say it has 0 mean, just for simplicity, yeah, or we have already subtracted the mean. So now we're going to find the direction with the greatest variance. Okay, so that means I'm taking a vector v that is some vector in my space. I can rotate it, I can turn it, and now I project my data onto that direction, right? So I take a line defined by that vector, right? The line spanned by that vector, and I just orthogonally project my data onto that line. Yeah. So a projection like that is given by a scalar product. So yeah, I'm projecting my points onto that line. And now so these are the projected points on the line. I take the squares and sum. So I'm computing their empirical variance. Okay. So I get a cloud of random data. I place a fixed line in that. I project all my data points onto that line. Now, if I just look at the line, I can think of that as one-dimensional random points. I compute the variance, the empirical variance of that sample. That's what I'm doing. Okay. So, and now I'm gonna change the vector v until this becomes maximal. I'm gonna rotate this vector, or rotate my projection direction until I get the largest variance. Okay. You can see that the maximum here is taken over all vectors of length 1. So why is that? That is because if I am allowed to change the length of this vector, then I can increase this variance here. I can cheat and just increase it by scaling the length of the vector up or down, right? I can increase or decrease the variance by making the vector shorter or longer. So in order to set a scale for this variance to make it comparable between different directions, I demand that the vector is normalized to 1. And so I only rotate, right? I'm only allowed to rotate. So I solve this optimization problem here. That gives me a direction. And in that direction, I get a variance value. So now basically I take my space and I collapse out that direction. I take the remaining space in all other directions. And in that subspace, I repeat the procedure and find the direction of largest variance in this. Right? And so one by one, I can find orthogonal direction of largest variance. And so, and I can do that, I can do that for all values, or can do that just up to some k, right? So, and if I do that up to k, if I have b dimensions, and I do that k times, right? Then I get k directions, and those k directions are the directions with the largest overall variance in my d-dimensional space, right? And I can project onto that subspace. And the projection onto that subspace, that is the PCA solution, right? Or depending on how you phrase it, the vectors that span that space, the set of vectors that you have found that way, that is your those are called the principal components. Yeah. So what is the idea behind this? The idea is you get data in a high dimensional space, and you want to do dimension reduction, right? You want to reduce the dimension. And that is, often if you get, somebody hands you a data set, I don't know whether any one of you has ever done practical data analysis, which is, by the way, a total pain. So somebody, you work, say, with some biologists, and they give you a spreadsheet, right? And they're like, this is what we've measured, right? Then you have this huge spreadsheet, and the columns have like some entries which are like 6-letter acronyms that you can't read, right? You're like, okay, what does this mean? Like somebody tells you, find signal in this data, right? So, I mean, what is the first thing you do? You try to look at it, right? So, of course, there are dangers in starting that way. I'm not going to get into that, but often for visualization, PCA is a really useful tool. If you just have a data set and you want to look at it, you can't plot a 10-dimensional data set. So you try to find some 2-dimensional summary of it or 3-dimensional summary of it that you can plot, right? PCA reduces dimension from, you can use it to reduce dimension from any number of dimensions to 2 or 3, and then you can plot. What you have to keep in mind is which implicit assumptions you're making when you do the dimension reduction, right? So in some sense, every dimension reduction method try to find subdimensions that are interesting. What is our measure of being interesting here? The measure of being interesting is simply large variance, right? So and the assumption there is you're looking for the dimensions where the action is in a sense, right? You're looking for the direction in which there is the most going on, the most variation. If those are the most interesting ones, then this is the right thing to do, right? But one thing you have to think carefully about is if your entries are, say, if this is really measurement data, right? Are the scales of that comparable, right? If one of those things is if one of those variables just lives on a much larger scale than the others, then PCA is always going to find that variable. Okay. So now this slide and the following one. This slide is basically all information that we already know from our Gaussian chapter. But this slide and the following one write out the PCA computations in terms of eigenvectors and eigenvalues, right? And so here is the matrix, right? And this is just the eigenequation. So here now the matrix is S, symmetric matrix. U is an eigenvector, and W is, or omega is the eigenvalue, right? And now imagine that we're thinking of this matrix as the covariance matrix or empirical covariance matrix of our data, right? So the actual covariance matrix is if the data is zero mean, take the outer product of a data point with itself, and then take its expectation, right? And so these brackets here are expectation. So this is a D by D matrix, and it's positive definite if your data is not degenerate on some subspace. So, and now you can write if you have a vector V, this is the vector that we want to project on, then we now know from our previous chapter that this matrix has an eigen O in B, right? So we can take the vector, the direction that we want to project on, and expand it in this eigen O in B. So, and then we get something like this here. So these are the coefficients of this vector, the entries with respect to the eigen O and B. And we can rewrite our original matrix like this here, right? So we take a diagonal matrix where the eigenvalues are on the diagonal, and then we have a transformation matrix here, right? So in our previous notation, so if this is a covariance matrix, this is a matrix where the variances of the decoupled directions are on the diagonal. And the U and the UT are the orthogonal transformation matrices that we get to that basis and back to the original basis. So, and if we now look at the variance in that direction, right? The variance is, so this is a projected one-dimensional variable that we projected on, now not on V, but we're just projecting on each eigendirection individually, right? If we project on the ith eigendirection, then we get a one-dimensional point on that direction. So that is the X transpose UI. And then we take the square of that because we're interested in a variance. So the expectation of that is going to be the variance, right? We can expand that like this here, right? We can expand the square into just two scalar products. And then you can do your scalar product arithmetic, right? And you have like so the UTX, that's an inner product, the XTU, that's an inner product, but then you can, because that's associative, you can read that as this here as the outer product matrix XXT. Yeah. So that outer product in expectation is exactly our matrix S, right? So what we get here is this. Then that is our eigenrepresentation, and that is just the eigenvalue. Okay, so the variance in this direction, the actual variance of x in the eigendirection is the eigenvalue. That is exactly what we have already seen before, just now applied to the PCA case, right? So if we project onto, if our vector that we project on is chosen exactly in direction of one of the eigenvectors of the covariance matrix, then the variance in that direction is just the eigenvalue. Okay. So, and now which direction are we going to get if we just choose the one with the largest variance? Exactly the eigenvector corresponding to the largest eigenvalue. Right? So, and you can prove that easily, but you can also just think intuitively, if I would move a little bit away from that direction, then I would interpolate it with the other directions, which all have smaller eigenvalues, right? So I would decrease my variance a little bit. So what that tells us is what PCA does is, in short, if we do dimension reduction with PCA to k dimensions, then what we're doing is we take the empirical covariance matrix of our data and find the k eigenvectors with the largest eigenvalues, and we project on those. So when we say largest eigenvalues, do we mean by magnitude? So in this case, fortunately, it doesn't matter because the covariance matrix is always positive semi-definite. And so there's never a negative eigenvalue. Yeah.
Question for when you have the point parameters, for example, the second step in top line,
this one here?
Yeah, isn't that just matrix multiplication? Like
so these here are an expectation, right? And this is a fairly common notation in machine learning. I prefer the E operator for expectation, right? Because it's literally a linear operator if you're a mathematician. But machine learning has a lot of influx, or like a lot of machine learning migrated from physics. And in physics, this is a very common notation, right? So you will see these notations interchangeable. Yeah. Okay, so now if you do this in practice, right? So you get your data set and you run your PCA algorithm. Then one thing is you can do is you can say, okay, I want to visualize. So I definitely want to have 2 dimensions, right? So I'm always projecting to 2 dimensions. So I always project to 3 dimensions. Yeah? Another thing you can do is you can try to figure out what a good dimension for your subspace is. So, and now if you assume that what is interesting is variance, then you would want to keep everything that has large variance and throw away everything that has small variance, right? So you can first do your change of basis into the eigenbasis, and then look at the eigenvalues and can just plot them, right? And that is done here for 2 different data sets. So here is the magnitude, the size of the eigenvalue, and the eigenvalues are just ranked by size, right? So they're just been sorted so that they get smaller and smaller as we go out here. And you can see that here for these 2 different data sets, we have in one case, we have a few large eigenvalues, and then it drops very sharply and all the other eigenvalues are small. And in this case here, the eigenvalues decay more gradually, right? So if we have this kind of sharp drop here, where we have a few large eigenvalues, and then it drops to something small, that is also known as a spectral gap, right? So the term spectral gap is kind of used in 2 ways. One is as the difference between the first and the second eigenvalue, and sometimes it's used for the gap between those eigenvalues that are large and those that are not large. Yeah, if there's a clearly expressed form of that. If you have something like that here, and you think that PCA is the right way to reduce dimension in your data, then you have a good answer, right? Then you should cut off here, right? Because then if you assume that high variance means interesting information, this means you keep all the interesting information, right? if you have something like this here, then you don't really know that clearly where you should go. Right? You're always going to lose something. Okay. So again, so what you do with principal component analysis is you find a subspace. And the way you find that subspace is by basically, first of all, you're approximating your data, which may not be Gaussian at all, right? You're approximating that by Gaussian, by saying everything that I analyze about it is summarized by its covariance structure, right? So one way of thinking about it is you say you take your data cloud and you first fit a Gaussian into it. So, and then you choose the directions of that Gaussian that in terms of this variance are the most interesting ones, right? And again, if you think back earlier, what we said earlier about that, we can always think of a Gaussian as being independent scalar variables in some coordinate system. And basically in that picture, what we're doing is we're changing to that coordinate system. And we're choosing the k out of those d variables that have the largest individual variances. That gives us a set of directions. So a k-dimensional subspace, we project to that subspace. So each data point is then associated with a lower dimensional k-dimensional projected data point, right? And there's various ways that you can apply this. You can use it for compression, right? Because what you've done here is you've taken a vector that has d entries and you've compressed it to a vector with k entries, right? You can use it for denoising if you think of those dimensions that you retain here as information and the remainder as noise, right? And you can use it for visualization, as we've mentioned, and for various other things. There's one thing that I want to mention. So an idea that keeps creeping up again and again is, so you want to say, do some form of supervised learning and say it's computationally intensive, right? For high dimensional inputs. Why don't we do PCA first and then do our supervised learning on the low dimensional? Yeah. So again, this is something that I can't make precise, but as a rule of thumb, I can, after enough years in this field, I can say with great confidence, if you do supervised learning after an unsupervised step, you're always going to lose out against a supervised learning algorithm that does not factor through something unsupervised. We're doing something unsupervised. When you have supervision information, you're always throwing away something. Okay, so if you have supervision information, you want to use it. And you do not want to just first do some unsupervised step. Yeah, I have never seen a single example where that ended up being a good idea. Yeah, maybe at some point somebody's going to prove me wrong, but I've just never, just empirically from my experience, take it or leave it. In my experience, that is a terrible idea. Doing something supervised first, unsupervised first, followed by something supervised, you're going to lose out. Okay, so here's a cute example of PCA that is not just denoising or something, but something you can visualize, right? And yeah.
That's great. About your information that you're going to use out in the time. What other ways would we have to reduce dimensionality of our data to make it?
What other ways do you have to reduce the dimensionality of the data? So my point is that if you want to follow up with a supervised step, I would find some way that does not do the dimension reduction first. The dimension reduction typically is unsupervised, right? And there are good reasons to use dimension reduction, like denoising, visualization, and so on. It's just if you want to have, if you want to then follow up with the supervised learning algorithm, give the supervised learning algorithm your entire data and not the dimension data. That's what I mean.
Apply to the autoencoders to then get the lane variable middle because that's a smaller dimension data set.
So would that also apply to the autoencoders? So So I would say this applies in cases where the thing that so let me make a distinction between use cases here, right? So two ways that you can use an algorithm like this. One in a more statistical sense, where you're looking for, say, a good prediction or the right answer to something, where there's some notion of truth, right? That's really more statistics. And then there's more the kind of the side of machine learning that you might say is a little more whimsical, like an image generator, where you just think one thing's to look good, right? This does not apply if you just want one thing's to look good. You do whatever works, right? So if you throw, and I mean, with the autoencoder, it depends also on your training pipeline, right? Do you overall use supervision information somewhere or do you not, right? So it's really at a very high level. If you are interested in accurate answers, if you have a notion of accuracy that you want to retain, doing something where you do something unsupervised that looks good to humans first tends to be a bad idea. A machine learning model that has access to all the information will win in the end. That's all I'm trying to say. Yeah.
Certainly, it's a good idea to use for surprise set. So, does that mean like even information about long variance in PCA could be benefit like the process later?
Yeah. So that's actually a good way of phrasing it. So the question here is, does it mean that even information that has low variance in PCA could be useful in the process later? That's exactly true, right? That is one failure mode of this, right? You throw away information because it has low variance in one direction, and PCA thinks, okay, that's worthless, right? But again, simplest example, if you're working with measurements here, and some of these measurements simply live on a larger length scale, then that's going to show up as a larger variance, right? But maybe that is not the interesting direction in your data, right? But PCA is going to throw it out. Now, in a supervised training process, a supervised model will pick up on that. It will notice, okay, the informative direction is actually another one. The informative information is actually somewhere else, right? Sorry. Yeah. Yeah. So if you normalize first, right? So if you scale all your variances, if you whiten, right? If you scale all your variances. So one problem with that is the only way you can normalize usually is like the data is, if the data is the only information you have, then by normalizing, you're basically making your Gaussian distribution spherical. So then PCA can't, then all the dimensions look the same to PCA, right? But there's a kind of, it's still like the question still hints at something else that is important. And that is, it's not just the meaning of the variance, it's also that you're assuming here that that information is only interesting, or your entire definition of information is Gaussian, right? If the distribution is highly non-Gaussian, then the variance is just not going to capture it regardless of how it is scaled. And that is something you're throwing away too. Yeah.
Just becomes every principal component map exactly onto one of the nodes in your latent layer. Do they carry the same amount of information?
Do they carry the same amount of information? Well, they do in the sense that you keep all those directions, right? I mean, you project something out, you get something k-dimensional, and information is either in there or it's not. So in a sense, yes, they do. But you do have this additional information of what are the variances, right? So you do have the information of like which dimension did your model think is more important or not. But if you just take the projected point as such, then the k directions are just in there or not, and they're not annotated by it. Yeah.
So let's say I have some way to constrain the latent dimension, like maybe and then I do the supervised learning so that the latent dimension aligns the goals of the supervised learning allows.
Well, so if you can use the supervision information in your dimension reduction, right? Then my point does not apply. Then you don't do an unsupervised step first, right? But PCA is unsupervised. Yeah. Okay, so here this example is an application of PCA that at some point became very fancy apparently in the field, and was called eigenfaces. And so what they did here is they said, okay, we're going to take a database of phase pictures, and they are somewhat standardized. So every picture has the same format. There's always a person in black and white, roughly the same size, centered in the image, right? And then they represented each of these pictures just as a grayscale vector, right? So you think of this as a matrix of pixels here, pixel values, and you just spool that matrix off into a long vector. So each image becomes one vector, right? If the image is, say, 16 by 16 pixels, you get a 256 dimensional vector. You just think of that as a point in 256 dimensional space. Yeah. So, and then they said, okay, now we can simply find the principal components of those vectors. Those are again vectors in the same high dimensional space. And then we can rearrange those into a matrix and we get a picture again. Plot that vector as a picture. So, and they take their image database with so and so many people, and then so now you go through this process, right? You write you encode each image as one long vector. In that high dimensional space, you do PCA. You find the direction with the largest eigenvalue. That's a vector. You rearrange that into a matrix, plot it as an image. This is what you get. Okay. So this is the first principal component of this phase image database. Okay. So it's kind of like the average phase in that database, right? But it's a very primitive way of taking an average. Right? And then you get the next principal component, and so on. Actually, the way they look, I guess, my best guess would be that maybe they're ordered this way. But so these are now, you can see that this is kind of something like a mean, and then these are different offsets from that mean, right? Different ways to offset from that. There was a time when machine learning and computer vision were so basic that this was a big deal. Yeah. So, and here's another application, and this is from science, and in the sciences, PCA is unbelievably. Yeah, the entire book's written about PCA. And if you look at like citation databases or something, among methods that are broadly part of statistics, PCA is definitely one of the most widely used ones in other fields, right? So, and here they do the following application. They look at genetic variation within Europe. So basically, they take a gene database, they do some form of genetic analysis on it. They encode that as a list of variables, and then just treat those as input to PCA. Yeah. So, and then they take literally the two first components of that and project them to that. Okay. So your input data is just lists of numbers that encode genetic properties. They're literally just measurement variables. You throw that into PCA, you take the first two components, project it on the plane, and plot it. And it turns out you get something that resembles the locations of where the genetic measurements were sampled on the map, right? So yeah, this is like, I don't know how much there's really in there scientifically, but this is the kind of publication that writes itself, right? Like, you get that picture, this is so going to get published, right? I mean, yeah. Oh, okay. But I mean, definitely, like, this is something where definitely that structure is not just random, right? There's signal here in those two components, sure. Okay, so I think I have to stop. Too bad. All right. So I think we have like 1 or 2 minutes if there are any further questions. Yeah.
Maybe I missed it, but when we maximize the likelihood and then we maximize the variance, is there like a direct link between maximizing the likelihood and maximizing the variance from the data.
So can you tell me which problem you're talking about, or which model?
Beginning of PCA, we had like the marginal distribution on X. Yeah.
Yes.
X. Yeah, we had this marginal distribution, and so we can maximum likelihood on it, and then we went to PCA where we maximize the variance, so it's like
yeah. So in this case here, we have, so PCA is what we get when we set this here to, when we take the limit of this psi to 0, right? So here we're asking what generally happens if we were to maximize the likelihood in this. Yeah. So, and then it turns out that in the specific case where you do PCA, where you take this to 0, the maximum likelihood estimate coincides with the PCA solution.
maximizing the variance.
Exactly. Yeah. All right. Then see you on Thursday.
Yeah.